Section 11.5 is about infinite geometric series. I'd like you to compare the two series here. We'll start with the one on the left. If you notice, we are adding values and they go on forever. And when we add those values, you see this table shows us the sum of those values, a half and then 0.75, 0.875, and so on. If you notice, the sum increasingly gets bigger and bigger and bigger, almost to the number 1, but it's never actually going to get there. And when you look at the graph here, you can see that the values are going to constantly get closer and closer to 1, but they're never actually going to arrive there. This is an infinite geometric series, except this one is called a partial sum because its value approaches a number, in this case 1, but it doesn't actually get there. And we call those a partial sum. We also call this a convergent series because it converges, the series converges on the number 1 in this case, but again it never actually gets there. This is one kind of infinite geometric series, and it happens when the common ratio is between -1 and +1. You get an infinite geometric series that has a partial sum, or we call it convergent. Now let's compare that to the one over here, and what happens here is the sum just keeps getting bigger. And if I increase n, if I increase the number of the value in the series, then the sum just goes off into this huge infinite number. And so there is no sum to this kind of series. And that happens when the common ratio, the absolute value of the common ratio, is bigger than 1, which means anything that's smaller than -1 or anything bigger than 1. If that's the case, that infinite geometric series has no sum. Now if I were to write the one over here in the same way in which I wrote the one on the right side, it would look like this. The absolute value of r is smaller than 1, or the absolute value of r is bigger than 1. One of them, again, has a partial sum, the other one has no sum. So here we see the formula for the sum of an infinite geometric series. Now this sum is for series that are convergent. They actually approach a value, and that again happens when the common ratio is between -1 and 1, or the other way to write this, as I did on the last slide, is the absolute value of r is smaller than 1. So when the series is convergent, this is the formula we use to find the sum. So if I want to come down here and find the sum of this geometric series, I first need to know what the r is. I need to know what the common ratio is to see if there even is a sum. The way you do that is you take each term and divide it by the one in front of it. And for that we would take 3/8 and multiply by the reciprocal. This will cancel here, giving me a 3/4. So to get from 1/2 to 3/8 we multiply by 3/4. Because we're told that it is an infinite geometric series, then we know that the common ratio is 3/4. Therefore it has a sum. We also know that a sub 1, the first term, is 1/2, and we're going to use that information to find the sum. So here the sum equals 1/2 over 1 minus r. My r is 3/4. If I do 1 minus 3/4, I get 1/4. So that's 1/2 times 4 over 1, which is 2. So the sum of this series is 2. This example over here, to get from 1 to -2 to +4 to -8, that's the series, I'm multiplying everything by -2. So my r is -2. Now because my r is not between -1 and 1, then I say no sum exists. This example is written in sigma notation. Remember, that's what this value means. This letter is that means the sum or the series of this sequence. And the infinity symbol means that the series is going to be infinite. So we're going to evaluate the sum of this infinite series. Now because of the way that we write the series, we know that a sub 1 is going to be 24. That's that initial value here. And the r is -1/5. Because my r is between -1 and 1, I know that the sum of this infinite series exists, so I'm going to use the formula. So the sum of 24 over 1 minus -1/5 makes that 24 over 6/5, makes that 24 times the reciprocal of 6/5, which is 5/6. 6 goes into 24 4 times, so we end up with 20. So the sum of this infinite series is 20. In this example, we're asked to write this repeating decimal as a fraction. It turns out that we can use the sum of an infinite series to find this. It's kind of interesting, so see if you can follow with what I'm doing. 0.039 repeating. What that really means is 0.039, 39, 39, and so on. Now I'm going to write that a different way as 0.39 plus 0.0039 plus 0.000039, and I could keep going with that. Okay, so if you agree with that and you follow along with that, now I'm going to take each one of these and write them as a fraction. This is 39 over 100. This is 39 over 10,000. And this one is 39 over 1 million. Now if I look at that and I think about it now as a series, can you agree that a sub 1 in the series is 39 over 100, and that the ratio is 1 over 100? Because if you take the first one and multiply it by 1 over 100, you get 2 more zeros on the bottom, which becomes 10,000. So if you can follow that this series has an a sub 1 of 39 over 100 and a ratio of 1 over 100, well, this ratio is between -1 and 1. Therefore, we should be able to find its sum using the formula. So a sub 1, 39 over 100, and all of that's over 1 minus 1 over 100. So now I have 39 over 99 100ths, which is 39 over 100 times 100 over 99. Those will cancel, and we get 39 over 99. So that's what 0.39 repeating is as a fraction. Now technically you should reduce this as 13 over 33. And so that would be our reduced answer. What I really want to show you though is any repeating decimal can be written by just dividing that number by the same number of 9s that come in the repeat. So another example of this, 0.25 repeating, is just 25 over 99. Because there are 2 values that are repeating, we use 2 values for our 9s in the denominator. And it works with anything. If I have 0.578 repeating, that's going to be 578 over 999. That would be the fraction there. If I have 0.6 repeating, that's just going to be 6 over 9. So anytime you want to write a repeating decimal, you take the number of repeats and divide that by the same number of 9s.